Hello, welcome to your online lecture for the course Pathophysiology 1. In today's lecture, we're covering cancer. There are two cancer lectures. In the first one today, these are the topics that we're going to be covering, and then in Cancer 2, we'll cover these topics. And we'll start off by identifying what is cancer. Here are some examples of how cancer looks. Cancer really are masses, and if you look, you can see where those masses are present within these different organs. We have the lung, we have bone, and we have the brain. And what cancer as a mass will do is it will expand in growth, it will invade normal tissue, and it will eventually destroy it. Lungs, though, the cancer can reside for quite some time before symptoms are even noticed. And then once symptoms do happen, then things become much more of a concern. But for instance, in the bone, you could have a mass of similar size as, say, in the lungs, but in the bone, and this is located right around the knee, this will weaken the overall structure. It can cause bone pain in this individual and even potentially lead to fractures, which would be called pathological fractures. And so this would be identified fairly quickly because of the bone pain that would exist. In the brain, you can see how this mass would easily compress neighboring structures of the brain. It would also cause an increase in intracranial pressure because that mass wasn't there to begin with, and our skull wasn't designed to have an increased mass present. So it would increase intracranial pressure, which can cause brain herniation. You can see it's putting pressure on surrounding structures and overall changing the appearance of the brain. And so these individuals would present usually with signs and symptoms that would indicate that there is something wrong. But the point here is that tumors of the same size can have different effects depending on which organ they're present in. If cancer of the lungs is still clinically silent, you can take an X-ray, if it was indicated, and you can see that it shows the cancer much nicer than you would otherwise know because it can be clinically silent. Adenopathy, which is enlarged lymph nodes. You can see in the neck and in this person's armpit, so the axillary lymph nodes. This is not necessarily indicative of cancer of the lymph nodes. It could be something such as a viral infection, and that's where complete histories and examinations, as well as physical examinations and palpating these lymph nodes and monitoring them to see if they, how they feel, but also if they change. And so although it could indicate lymphoma, which is cancer of the lymph nodes, it may not be. Here we have a melanoma, which is called malignant melanoma. And this is a very aggressive type of skin cancer. It spreads very quickly and metastasizes quickly. It may not be noticed by a person, though. If this is present on their back, they may not even notice it, and they may not have any signs or symptoms that it's actually spread through their body until they have problems in other areas of their body that the cancer has spread to. Here we have cancer of the colon detected by colonoscopy. And you can see here the presence of cancer in the lungs, much more evident on an X-ray because you're not going to be getting an image such as this of an individual. And the point here is that cancer can come in so many different forms clinically. And depending on the type of cancer, and as mentioned on the last slide, depending on the location of cancer, it can present very differently. So that's a very important consideration. Now let's have a look at how cancer is diagnosed very briefly. The masses that contain cancer cells need to be looked at under a microscope to show the cytology. And here you can see some examples of cancer histology. This is normal prostate tissue, and you can see some of the changes that can occur as cancer progresses. And we'll look a little bit more closely at this on an upcoming slide. At the bottom here, we can see what would represent a mass. And this here is cancer, but if you look closely, you can see that although many of the cells are cancer cells, not all of them are. We still have the presence of fibroblasts and macrophages, T cells, even blood vessels that now belong to that mass. And this is collectively referred to as the stroma. And the stroma is really the supportive tissue of this tumor in this example that consists of the many different cells that I mentioned and also blood vessels. And we'll look at the importance of blood vessel supply to a tumor shortly. So the next handful of slides are going to be talking about cancer in Canada. So we're going to be looking at epidemiology, and I'll be very clear with what specific details you need to be aware of because some of the slides are quite dense. This slide shows you the different causes of death in individuals within Canada in 2012. And what you probably can notice right away is that half of all deaths are due to cancer and heart disease. And it wasn't that long ago that heart disease was actually the #1 killer, but now it's cancer. So cancer is the #1 cause of death in Canada. But why? Well, a couple of reasons. One, our population is living longer, and cancer is in a lot of ways considered a disease of aging. So if people are living longer and they become older, they're more likely to have cancer rather than, say, dying in their 70s and cancer never actually presenting itself because it didn't have the chance. And so with heart disease, when it used to be the #1 cause and now it's not, well, partly because cancer seems to be increasing in terms of it causing death, but with heart disease, we're generally getting better, more in certain areas of the world than others, at exercising more and eating better and making better choices to keep our heart healthy because there's a lot more education now, a lot more public health initiatives. I'd like to bring your attention to the orange circle as well as the gray circle on this image. The orange circle is speaking about incidence, and incidence is the rate of new, or you could say newly diagnosed cases of a disease, in this case cancer. And so it's usually reported as the number of new cases occurring within a specific period of time. So in this case, it's referencing the number of new cases that will be diagnosed in 2016. Whereas the gray box is referring to mortality, so the number of people who die from cancer. What we can take from this is that every year, over 202,000 Canadians are diagnosed with cancer. And so if we look at this from a per day perspective, since this is referring to per year, over 202,000 are diagnosed with cancer, then if we look at it per day, we can say that 555 Canadians will be diagnosed with cancer every single day. And we can say, looking at the gray circle, 78,800 Canadians will die of cancer in 2016. So on a per day, that's 216 Canadians that will die of cancer per day in 2016. And so those are very scary statistics, especially when you look at it on from a daily basis perspective. Now, what's important to know is that we can't directly necessarily relate these two and say that of 202,000, 78,000 died, because we don't know necessarily how long that these people had cancer for. Maybe they were diagnosed many years prior, but regardless, very staggering statistics. Looking at the left slide here, we're looking at, again, new cancer cases. So we're referring here to incidence, the number of new cancer cases, and it's separated by sex. So you can see here that there are more new cases of males being diagnosed with cancer than there are females. The second important information to let you know about is that the number one cancer diagnosed in men is prostate cancer, and the number one in women is breast cancer. And you can see it's number one by quite a bit. But from there, the second most common cancer in men is colorectal cancer, whereas in women, it's lung cancer or lung-related cancer. And then in males, the third would be lung cancer, and in women, colorectal cancer. So these are the statistics that I would like you to be aware of. You don't need to know the numbers, but be aware of what the most common cancer is. You need to know the top 3 for males and females. And then overall, the top 4 being prostate, breast, lung, and colorectal cancer. On the right, you can see the increase in that the new cases diagnosed is increasing. But these graphs can be interpreted in many ways. Can we say that, is it because people are living longer that we're seeing more cancer cases? Is it because of our environment? Is it because we're better at diagnosing cancer? There's many different variables that are very important to consider, but you can see that overall general trend. And we're speaking here of all cancer, so it's not a very specific graph. This graph here shows the overall trends in both incidence and mortality. So remember, incidence refers to number of new cases, mortality refers to death, relating, of course, to cancer, specifically all cancers. And overall cancer mortality, so we're looking at the dashed line in both males and females, you can see that overall it is on the decline in terms of mortality. But in terms of incidence, so now we're looking at the solid line, you can see that in men, if we head over here, it's relatively stable, but you can see that it is starting to decline. But in women, you'll notice that it's slowly starting to increase in terms of incidence. And the reason for that, the reason that it's increasing with women, is because mainly of lung cancer. Because women started smoking later than men did. Women started smoking probably in and around the 1960s, so it was really a male-dominated habit until around the 1960s when women started smoking. And so then naturally, if they started later, then their cancer will also show up later in women than in men. So the trend in women should eventually be similar at some point to men, but hopefully overall both will continue to decrease as people start making better choices. In each age range, there are different cancers that appear, and so this slide shows you the breakdown of cancers according to age and the percent number of cases. So let's look at the left column to start. Children, so from age 0 to age 14, so children and early teens, the biggest cancer is leukemia. And then you can see, looking throughout, that this isn't really evident as anything major. I mean, we drop down big time once we're into mid to late teens, into up to the late 20s. And then it kind of disappears and it's not very evident. From age 15 to 29, you can see that both thyroid and testicular cancer, as well as Hodgkin's lymphoma, are the most common. From age 30 to 49, thyroid is still an issue here, but the greatest concern is breast cancer. From age 50 to 69, you can see prostate cancer really seems to appear. Breast cancer, still a problem. Lung cancer, and colorectal cancer. And then from 70 and up, you can see that lung, colorectal, breast, and prostate cancer, still a problem. And so from our earlier slide today, you already learned that breast cancer, prostate cancer, colorectal cancer, and lung cancer are the top cancers affecting men and women. Of course, men for prostate, women for breast. But you should be aware of the main cancers that inflict this age group as well. So not all of them, just the main ones as discussed. And this is important because when you're aware of the age of an individual, you can narrow down the likelihood of the cancer that they may have. One of the problems with lung cancer caused by smoking is that it doesn't really become evident until age 50. Right? You can see that's such a small percentage before that. And so what's difficult with our youth today that begin smoking is if you tell them, okay, when you're 50, you could have cancer, or when you're 70, you could have cancer. They don't really care. Kids aren't scared about a future that's so far away. And so even though a lot of the changes are occurring within the cells of their lungs when they start smoking, it isn't until later on that they could potentially become diagnosed with cancer. Lung cancer. This here is our final slide on epidemiology, and this is showing you the incidence in different areas of Canada. Most new cases are in Ontario, as you can see, and that's because of our larger population. But if we were to adjust for population, the West Coast has less cancer than the East Coast when you've done this adjustment for population. They also have an increase in diabetes as well as obesity compared to other areas as well. All right, now let's get to cancer, move away from epidemiology and talk about some terminology that's important in order to understand cancer. The word tumor originally referred to any swelling that was caused by inflammation, but now the word tumor is generally reserved for describing a new growth, which is called a neoplasm. Okay, so here we have a tissue or overgrowth, a neoplasm. Neo means new, so new growth. Now I'm going to give you a little bit more elaborate definition on tumor, and you don't need to actually write the whole definition down, but just listen to some of the key words. So a tumor is considered a tissue overgrowth that is independent of the laws governing the remainder of the body. And the difference between tumors and reparative processes, such as, let's say, a bone callus, is that the neoplasm overgrowth serves no useful purpose to the organism. Okay, so there's no useful process, no physiological purpose that benefits our body. So what we can say in general then is a tumor is an abnormal growth resulting from uncontrolled proliferation, which really serves no physiological or beneficial function to our body. Now the term cancer refers to a malignant neoplasm, so a malignant new growth, and is not used to refer to benign growths. And we'll talk about some examples shortly. So I don't want you to have the misconception though when we say that malignant is different than benign. We associate malignant as bad and benign as not bad. I don't want you to have that association or misconception that benign is good or okay. It's important for you to recognize that even a benign tumor can become life-threatening should it enlarge enough in a critical area. So just because it can't spread and just because it's not destroying tissue in the area, it doesn't mean that it won't cause problems. So for example, if you have a benign neoplasm within your brain, it can put pressure on surrounding structures. It can increase what's called intracranial pressure. Or if you had a tumor in the heart, it could impact how the heart actually functions. Okay, but when we do talk about malignant, we are referring to cancer. All benign tumors are going to be named according to the origin of that benign tumor, and it's going to have the suffix "oma." And so you can see "oma" written here. And so here's some examples. Lipoma is a fatty tumor. A myoma, this refers to muscle. So myoma is a benign tumor composed partly of muscular tissue. A leiomyoma is a benign tumor of smooth muscle. An adenoma is a benign tumor of glands, such as the prostate gland. It could be glands within the breast, mammary glands. It could be glands found within the pancreas or any glandular tissue. But the point here is you can see the origination of that tumor, whether it's fat tissue or muscle tissue, and then it has the suffix "oma." But you can see that once we move on to malignant tumors, although they are still named by origin and suffix as well, they're stated a little bit differently. And we'll use terms such as carcinoma and sarcoma versus just using "oma" like we do for benign tumors. So let's say in this example here we have a adenoma, which we know is a benign tumor of glandular tissue, but if we call it an adenocarcinoma, then this means that it's a malignant tumor of glandular tissue. And when we use the term carcinoma, it's a type of epithelial cancer, so cancer that's affecting epithelial cells. When we use the term sarcoma, we're looking at connective tissue rather than epithelial tissue. And so, for example, a lipoma here is a benign tumor from fatty tissue, arising from fatty tissue, but a liposarcoma is cancer. Whereas also cancer of muscle, and then myosarcoma has to do with cancer of smooth muscle, as already mentioned. Let us now look and compare or look at the differences between benign and malignant tumors. And I'm going to be reading, for the most part, off of this slide some of the important characteristics that help us differentiate between the two. With benign tumors, or let's start with the characteristic, growth rate. Benign tumors tend to grow slowly, and they have what's called a low mitotic index compared to malignant tumors that grow much faster, and they have a high mitotic index. A mitotic index is defined as the ratio between the number of cells in a population undergoing mitosis to the number of cells in a population not undergoing mitosis. That's mitotic index. In terms of border, benign tumors tend to be very well defined in their border. They have a well-defined capsule, whereas malignant tumors, they're not encapsulated, very ill-defined borders, looking a lot more concerning. In terms of invasion, benign tumors do not invade tissue in the area. They may grow and push tissue aside, but they're not invading tissue, whereas malignant tumors will invade and will destroy local tissues and cause what we know is of cell death is called necrosis. In terms of appearance, looking at benign tumors, they generally look like the tissue from which they arise, and we'll look at an image of that shortly, or at some point in the term, where they look very similar to the tissue that they came from. So if it's a benign tumor of skeletal muscle, for example, the benign tumor tends to look very similar to that skeletal muscle, but still different. But benign tumors are considered well differentiated. And that means that, remember, when we have stem cells, and stem cells will over time differentiate and become a very specialized cell, one that is well differentiated. So you might have a stem cell that becomes a cell that's meant to be part of the kidney. It's well differentiated. But with benign tumors, they tend to keep their differentiation. So when looking at these tumors, the cells tend to look like the tumor that they arise from. And so you could look at these cells and have an idea of where that cancer originated. Whereas with malignant tumors, they tend not to look like the tissue of origin. They tend to become less and less and less differentiated, and they can get to the point where they are undifferentiated, and you look at that tissue, and unless you knew the history of that individual and where that tissue was coming, had been biopsied from, you may never know what part of the body and what organ that biopsy was from, because it looks nothing like its tissue of origin eventually. In terms of ability to metastasize, benign do not spread to other organs, and we know they're not invasive. Whereas with malignant tumors, they have the ability to spread. We know they can invade and destroy local tissues, but they can spread to other organs as well, and this is called metastasis. And so you can have cancer of one organ that spreads to an entirely different organ. Now we'll look at the biology of cancer cells. This slide is showing you normal cells and cancerous cells, and you can tell right away that cancer cells look different from normal cells. They exhibit what we could call atypia. Some of the differences that we can see here is the cytoplasm is a lot smaller in the cancer cells. There are multiple nuclei that are present, as you can see. The chromatin within is a lot more coarse or dense, and that's because the cancer cells have a lot more DNA, so the chromatin appears a lot more coarse and dense. Malignant cells also exhibit what's called pleomorphism. And pleomorphism is where you would see variability in size and shape of these cells. So in terms of what pleomorphism actually means, it's the ability of a microorganism, or we could say in this case a cancer cell, to alter their shape or size. So much differences between normal and cancerous cells. Cancer is considered to be a clonal disease. Cancer starts with one cell. So if you have a whole bunch of different cells here within a tissue, you can see the one cell that it starts with, the one red cell. It arises. Then it starts dividing, or we can say it starts cloning itself and replacing the normal tissue. And you can see that happening here. And they can even form subclones, so kind of variations in their clones, but slowly but surely, or quickly, depending on the time that this actually is happening, is that they can replace normal tissue. Let's look at some of the abnormal growth features of cancer. So we're looking at how cancer cells behave, but we're comparing them to normal cells. So when you're looking at A here we have a dish that we have cells in. Normal cells growing in a dish will end up forming this monolayer. Okay, so one layer. And once they form this monolayer, they've realized they formed the monolayer, and they stop dividing. And the reason that they realize that they've formed this monolayer and they know to stop dividing is because of something called contact inhibition. Cancer cells, though, don't possess this feature, hence the multiple layers that you can see. So we can say then that cancer cells have loss of contact inhibition. Now, in looking at B, if normal cells will always have to be attached to something. So if they're suspended, like they are in this image here, they're suspended in a soft agar, they cannot attach to each other, they cannot attach to something, and therefore they end up not proliferating. And this is called anchorage dependence. So normal cells then require anchor or are anchorage dependent in order to grow and divide. But cancer cells don't need this. They can grow in substances that normal cells cannot. So we can say then that cancer cells are anchorage independent. And so to summarize what I just said in really two statements, cancer cells have these abnormal growth features. And the two main features that you need to be aware of is that cancer cells have loss of contact inhibition, and they also have anchorage independence. Remember that I recently mentioned the term differentiation, and I had said that stem cells will become very specialized cells. So tissues of your intestinal tract, for instance, are well differentiated and specialized to their particular function that they would have within the intestinal tract. But cancer cells have this loss of differentiation, or de-differentiation as stated on the slide, okay, cancer cells. So we go from differentiated to losing differentiation. In the top diagram here, you can see this representing here normal skeletal muscle. It's very organized, it's very well defined. But then in this diagram here, you can see what's called rhabdomyosarcoma. Rhabdomyosarcoma is a cancer of skeletal muscle. And you can see when you compare the two here, I mean, this looks nothing like the original tissue. And when I mentioned to you earlier that benign tumors tend to resemble, I don't have an image of it, I don't believe in this lecture, but if you were to see a benign tumor of skeletal muscle, you would see that although it looks different, it still resembles the normal tissue. But with malignant tumors, with cancer, that's completely different. You can see there's complete loss of organization. You can see very large and multiple nuclei that are present. You can see this real abnormal proliferation. You can see that you could hopefully understand that there'd be a high mitotic index. It looks very disorganized. And so we call this loss of differentiation or de-differentiation that occurs from the cancer. In this bottom diagram here, this is representing normal prostate tissue, fully differentiated. But as cancer progresses, you can see that we end up with a malignant tumor. Okay, so we're comparing to normal. A malignant tumor, but it's still well differentiated. But it's hard to catch it at this point. So you can see that with progression, we are continually losing differentiation. So we have poorly differentiated tissue, really starting to take on a completely different look. Whereas here, we have aplastic malignant. Sorry, anaplastic malignant. And what anaplasia is just loss of differentiation. So loss of the process of having these specialized function and organization. So this tissue could not perform the same functions as this normal tissue could. And the more undifferentiated, the more aggressive. And so we can look here at tumor grading then. And with these bottom images, we could refer to this as being, let's clear this, tumor grade 1, so grade 1, well differentiated. Grade 2, poorly differentiated. And grade 3 would be more aggressive, survival rate decreases, and this is where that cell has completely lost its differentiation. So it can be called anaplastic malignant, which is really an undifferentiated tissue. And grading is an important clinical feature that can help guide treatment depending on what grade somebody is in. So let's talk about the altered metabolism of cancer. The use of oxygen in cancer cells is quite interesting. Normally, and this is a review from normal anatomy, so we're looking at differentiated tissue, so specific tissue, specialized tissue. Normally our cells undergo what's called oxidative phosphorylation for energy. So this is where we take glucose that we've ingested and we use it to make ATP. So oxidative phosphorylation will produce at least 36 ATP because of the presence of oxygen. But without oxygen, we use anaerobic glycolysis and we only produce 2 ATP. And this, so you know, is per glucose molecule that's taken in. We can produce up to 36 ATP if oxygen is present, 2 if not. Now, tumors and other proliferative tissue will use anaerobic glycolysis. And this is called the Warburg effect, named after the person that identified it. And with glycolysis, we do know, you should recall, that lactate is a byproduct. But what's interesting about tumors is tumors can actually use lactate as a building block for the tumor, allowing it to proliferate rapidly. So once again, the Warburg effect. And this process will actually cause the doubling of the normal 2 ATP that we would produce from anaerobic glycolysis to 4 ATP produced when tumor cells and proliferative tissue use lactate as really a building block. Now, cancer cells will be in anaerobic mode. These cells don't need much oxygen and they constantly produce lactate, as I mentioned, and this is advantageous. It means that they can survive in an environment that other cells wouldn't be able to. Healthy cells couldn't. So cancer cells are always in a hypoxic state, but eventually when the cancer gets big enough, it needs, as you'll see, it will need its own blood supply for continued survival. Cancer cells do have genetic alterations that occur. And so when we have a normal cell, we have normal DNA, normal chromosomes. But in cancer, we have mutations. And so as cancer develops, it's important for you to know that it will accumulate more and more mutations. So you can see we have the first mutation, the second mutation, the third mutation, the fourth mutation, and now we have cancer cells. Okay, so we start with initiation, promotion, and then progression. And so you can see here that in order for cancer to develop, we require to have at least 4 or so mutations to occur. Cancer cells also possess what's called genomic instability. The DNA of cancer cells it's very unstable. They don't have a good repair process. They don't have apoptosis where, if something goes wrong, they die. They have a lot of DNA, and they have a lot of alterations of the DNA and the chromosomes that are present, and they could be numerical or they could be structural in terms of their alterations. And so this whole idea here is associated with what we introduced earlier about cloning, what would be called clonal proliferation. And so if there's enough mutations, then malignancy can occur. This diagram here is the clonal proliferation model of neoplastic growth. And these are specifically colonocytes, so sites of the cells of the colon, and you can see that it all starts with one cell. Then we have the first mutation. And you can see here that this mutated cell can reproduce itself, but it can also undergo another mutation and a third mutation, and then a fourth mutation, producing that malignant cell. Let's talk about another few terms that you need to be aware of when it comes to the concept of oncogene activation. Let's start with oncogene. An oncogene is a gene that in certain circumstances can transform a cell into a tumor cell. The cell ends up being kind of forced to mutate out of control. And so we can state then that it's a mutant gene. It could be amplified or overexpressed proto-oncogene. And we'll talk about what a proto-oncogene is shortly. But what I want you to make note of is that an oncogene is a gene that has the potential to become cancer. A proto-oncogene, this is a gene that, it's a normal gene, but it codes for proteins within our body that help regulate cell growth and differentiation. So it's, once again, it's a normal gene, but a proto-oncogene could become an oncogene, depending on the amount of mutations that are present or, increased expression or amplification. Now, tumor suppressor gene. Tumor suppressor gene, or sometimes called, and this may be helpful for your studying, sometimes called an anti-oncogene, is a gene that protects a cell from progressing to cancer. So when the tumor suppressor gene itself mutates and it loses it's reduced in its function, then cells can progress to cancer because they don't have that suppressor gene to stop it. So this gene here, if it's not working properly, maybe it's silenced, this is not good. We want this gene to be working properly. The term amplified here, over-amplified, refers to making many copies, whereas overexpressed refers to genes being turned on all of the time. So looking at this diagram here, we can see this normal proto-oncogene. And what we just spoke about, there could be a mutation, there could be gene amplification, or there could be chromosomal translocation. Remember, chromosomal translocation refers to part of one chromosome breaking off and then joining in with another chromosome. It's translocating. Okay, let's spend a few minutes talking about tumor-induced angiogenesis. First of all, what does angiogenesis mean? Well, genesis is formation of. Angio refers to blood vessels, so this is the formation of new blood vessels. And tumor-induced means that the tumor itself is creating its own blood cells or blood vessels. Now, if cancers are to grow larger than about 1 millimeter in diameter, they can no longer remain in their hypoxic state, and they need their own blood supply. They need more oxygen, they need nutrients for survival. However, in adults, new blood vessel growth is normally limited to areas of, let's say, wound healing. Another example would be at certain stages of the female's menstrual cycle. So really small cancers, they lack the ability to grow new blood vessels, and because of that, they may never grow larger than a grain of sand. But more advanced cancers can secrete multiple factors that stimulate new growth of blood vessels. And this we call angiogenesis. Sometimes you'll see it written as neovascularization, so neo being new, vascularization referring to new vessels or referring to vessels. And so this image here is showing you tumor-induced angiogenesis. And what you can see here with this tumor is that it starts secreting these factors. These are growth factors. So the different ones we have here are vascular endothelial growth factor, we have platelet-derived growth factor, and we have basic fibroblast growth factor. And these factors are actually secreted by the tumor itself in order to begin the process of forming its own blood supply. So it almost like it starts to steal and it's like it's stealing part of the blood supply from our vessels that would normally not supply that area. Or we could say that this tumor is essentially encouraging blood vessel formation using the local endothelial cells in the area. And so what this does is it leads to thriving of the cancer, but also growth of the cancer. And so figuring out how big a tumor might grow could actually depend, and how quickly, could depend on how many growth factors, what quantity of growth factors that tumor is actually releasing. And if it's a lot, well, then they're going to end up with greater blood supply, and then this could contribute to faster growth or speed of metastasis. And so this is a scary stage here. But nowadays there are drugs that you can give that are called anti-angiogenic drugs that will block the formation of new blood vessels, trying to keep that cancer contained. In this image, you can see two different diagrams, and they're actually entirely different processes. On the left, this is showing you wound healing. So here's a wound. And on the right, it's showing you malignant angiogenesis. And here is the wound, and here is the malignant tumor. And it's interesting because if you look at both of these entirely different processes, you can see that many similar processes occur. But when we look at the malignant side, you can see that there's extensive blood vessel formation. And even though we'll get angiogenesis when there's wound healing and repair, you can see the extensiveness when it comes to a tumor. You can see that it's a lot more destructive. So look what it's doing, how invasive it is to the area, how much the basement membrane is starting to dissolute. And we're getting further invasion. You can see the presence of the cancer actually infiltrating the area, so metastasis. And when I spoke about VEGF, so vascular endothelial growth factor, it's interesting because the tumor cell will secrete this, but this will also be used in the promotion of healing and producing new blood vessels and wound healing. So it's used in both wound healing in terms of angiogenesis as well as angiogenesis from malignant tumors. And so this all through it here would be considered the stroma, as mentioned earlier in today's lecture. This slide shows the hallmarks of cancer. Cancer requires alterations in specific pathways during their evolution. The 6 key pathways that must be altered are shown at the top of the circle. And beneath that, at the bottom of the circle, are considered the supporting pathways that would support the growth of cancer. And mutation in key genes often will alter several of these pathways. So let's talk about the top of the circle. We're not going to go into detail at the bottom. At the top, in order for cancer to develop, it must possess sustained angiogenesis, meaning that it needs to have the ability to form new blood vessels for its survival and growth. Tissue invasion and metastasis, it needs to have the ability to invade tissue and then spread. It needs to evade apoptosis, meaning that it really needs to escape cell death. It needs to have self-sufficiency of growth signals, meaning it needs to be able to produce its own growth factors to promote its growth, because the rest of the body doesn't really want to support it. It needs to have insensitivity to anti-growth factors, so it needs to be able to resist the signals that inhibit or are attempting to inhibit their growth, signals that normal cells are very sensitive to. And finally, it needs to have limitless replicative potential, meaning that it continue to replicate without limit. That's the end of today's lecture. Thank you for listening.